Alright, so moving on to the short-term behavior of rational functions, we already know that for the short-term behavior of polynomials, that's totally determined by uh, the roots of the polynomial, or when that thing is zero and how it's zero, whether or not the multiplicity or the power related to the roots are even or odd. So the exact same thing happens to rational functions. So let's take a look at an example of a rational function here. Let's take a look maybe at maybe x minus 3 times x plus 1 divided by, well, let's start maybe with x minus 2. All right. So first of all, we notice that this thing is still 0 when x is negative 1 and when x is 3. And the reason for that is when I plug in 1 or 3, this numerator is still 0, and then 0 divided by the denominator, whatever values it takes on then, those things get, that thing is still 0, right? You take 0 divided by something, you still have 0. So that's what happens with the zeros of the numerator. 0 divided by anything is 0. Now what happens when x is 2? Well, when x is 2, the denominator is 0, the numerator is negative 1 times 3, so it's negative 3. And negative 3 divided by 0 is undefined. So what happens in this case? Well, we notice that if I take numbers slightly before 2, so I'm going to graph the points A, R of A here, and I'm going to make 2 the upper bound of this thing. I'm going to make 1 the lower bound. As I start to move towards 2, its values get smaller and smaller. And why is that? Well, it's because this numerator here gets closer and closer to 3, sorry, to negative 3, but the denominator here gets closer and closer to 0. But we should make a note here. Right? This thing gets closer and closer to 3. It gets smaller and smaller, right? And my denominators get closer and closer to 0. So I'm taking these numbers that are approaching 3 and divided by smaller and smaller fractions, the whole thing gets bigger and bigger and bigger, right? And as the whole thing gets bigger and bigger and bigger, this thing starts to zoom up towards positive infinity. All right? All right, and at this point, this thing's pretty close to negative 3, and this thing's pretty close to 0. But since they're both negative, when I take their quotient, it's positive, and since the magnitude of this thing will be large, it goes out to positive infinity. Now, let's see what happens when I make my lower bound 2 and my upper bound 3. Let's get close to 3. Well, the same thing here, right? As I move in towards this thing, my numerator gets closer and closer to negative 3, and my denominator also gets closer and closer to 0, except now when I take a positive or a number bigger than 2 minus 2, these values are positive, so when I take their quotient, it's negative, and so that heads down to minus infinity. So what we have here is a vertical asymptote at x equals 2. A vertical asymptote just means a vertical line that this function approaches but never touches, right? It never actually touches this line, but it gets close to it in both directions. Now, we notice here that this thing changes signs, right? It's positive here and it's negative here. How can I get them to go in the same direction? And the idea is exactly the same as with polynomials. Things go in the same direction, or things don't change sign when your powers associated with are even. So if this thing's even here, then it's not allowed to change sign. So it's not allowed to change the sign of the function, right? If I now stick a squared here, then this numerator is always negative as you're close to 2. The denominator is always going to be positive. And oops, I'm moving the wrong thing here. Let's set this back. Let's just kill that. We get the idea. So as we pull it down here, it's negative from that end, and it's negative from the other end too, right? Because the whole thing is still a negative divided by a positive no matter what. So you still get zeros in the numerator the way you expect them to. They still bounce or cross in the same way that they do. See, we notice here that we cross in both directions. But if I made the x plus 1 a squared, now it bounces here, right? And then it still crosses here. If I made this a squared, they both bounce. And if my asymptote at 2 still, if I made this a cubed, then it bounces here, right? Because they're still supposed to bounce. And this thing changes sign. So the bouncing, the crossings really all behave the same as they did with polynomials, except that instead of having a 0 when your denominator is 0, you're having an asymptote with these infinity limits instead.